Hey guys, welcome to this new series where we deep dive into operating systems. In the last video, we looked at what operating systems are and we looked at a basic concept called virtualization. In this video, we are going to be diving deep into how this virtualization actually happens and how, when you seemingly just have one core CPU, and since a core can only run one line of instruction at a time, how does the operating system enable the CPU to run multiple programs concurrently? This is achieved by something called time sharing. So when I said that a CPU can only run one instruction at a time, it doesn't mean that instruction is an entire program, right? A program is a set of instructions. So what it can do is, when program 1 is waiting for something else to happen, it can immediately switch to program 2, run it, and then come back to program 1 to resume execution when whatever we were waiting for was done. Let's take an example. Let's take a single core machine and we have one program which is ready to run. What happens is, in this program, let's assume you have 5 lines of code which does some kind of computation, and in the 6th line you're writing the output of the computation to a file, and then you have 5 more lines of code which is doing some computation. When the CPU starts running this, what happens is the CPU runs the first 5 lines continuously back to back. When it comes to the 6th line, the CPU now cannot actually write something to the disk. The CPU itself cannot do that. So what it does is, the operating system tells the microprocessor inside your hard disk to do the work. The work is done by the hard disk itself. There's a microprocessor inside the hard disk which does the work. So the CPU says, okay, I have this piece of value data, write this to the disk in some block. Now the work is actually done by the hard disk. Let's say this takes some 10 milliseconds to write. In this 10 milliseconds, while the hard disk is busy writing, your CPU is idle because it needs to make sure the write is done before the program can move on to the next line. CPU now here waits for 10 milliseconds idly. Once the microprocessor inside the hard disk says, okay, I am done, back to the OS. Now the OS then tells the CPU to run the next 5 lines, which is computation. So here, if you see, the CPU ran the first 5 lines, it had to wait for 10 milliseconds for the data to be written to the hard disk, and then it runs the next second set of 5 lines. So here, although it looks like simple to us, there's a big problem here. Those 10 milliseconds that the CPU was waiting, that's wasted time, that's wasted utilization of resource. Let's say now here there are 2 programs, okay, which are waiting to run by the CPU. Now again, we're assuming a single core CPU, right? And what happens is, in this 10 seconds that program 1 was waiting for the write to be done in the hard disk, what the operating system actually does is, it says, okay, now the CPU is waiting idle. Why should it wait idle? There is a second program which wants to run. I'll start running that program now. It'll start running that program. Again, in program 2 also, program 2 and program 1 are similar, right? When the first 5 lines of program 2 are executed, and then the program is waiting for the disk IO to be done. Now the operating system knows, okay, here again we have to wait for a while. Let me switch back to program 1. So the operating system keeps switching back and forward between different programs, and it executes programs this way. So it gives you the illusion that 2 programs are running at the same time. By the time program 1 ends and program 2 ends, there will be very slight difference. If they run sequentially, let's say program 1 takes 20 milliseconds to run and program 2 takes 20 milliseconds to run as a whole. If it's run sequentially, finishing those 2 programs would take 40 milliseconds. But here, since the 10 milliseconds we were waiting, we started running program 2, right? Here it actually wouldn't take 40 milliseconds. It'll take much less than that, right? It'll only take 30 milliseconds. Now it might say 10 milliseconds. What is the big saving here, right? This is just one example. Now when you have hundreds and hundreds of programs running, this starts to add up, okay? And this is how your operating system, even though you have one core and you can only run one line of code at a time, it makes sure that the CPU doesn't spend any time idle if it doesn't have to. If there's nothing to run, if there's nothing to do, then your CPU will be idle. But if there are things waiting, your operating system makes sure that your CPU never gets idle. Because any IO, input-output operation done, is not being done by the CPU itself. It is being done by the respective microprocessor inside the hardware. For example, if you want to print, your operating system signals the printer, this is something I want to print, and sends over the data. That's it. Now the printing job is done by the printer. Until then, if you make your CPU wait, now that's time you're wasting. Instead of making the CPU wait for it idly, put the first program on halt, start running the second program. This is how operating system optimizes multiple programs to run in a single processor, in a single core. this is how it also brings the fact of illusion and virtualization, because whenever a single program is running, it has the entire CPU to itself. But in actuality, by the time it runs, by the time of program 1 completed, it actually shared the CPU with program 2, even though it didn't know. But whenever it runs, it has the entire CPU to itself. You understand? This is how virtualization of CPU, which we talked about in the previous video, comes into picture. Right? Again, if you haven't watched my previous video, go watch it, because understanding what we spoke about virtualization is important to understand what we're looking into here. So this is the so-called time sharing algorithm. But okay, now if we have two programs, I said okay, CPU, the OS tells program 1 to run and then program 2 runs when CPU is idle. But then how would you decide if you have 10 programs, 20 programs, 30 programs? How do you decide which program to run first? Let's say you've chosen a program to run first and now it's waiting for an input-output operation. How do you choose which program to now use the CPU now? This is dictated by the so-called scheduling policy. There are so many different algorithms for it, but the general term for this is called the scheduling policy. Right? There are so many different scheduling policies. We will look at each of them in detail. The scheduling policy is the one that figures out, okay, this is the next program that I want to run. Okay, now this is the next program that I want to run.